In Chapter 9, we're going to spend some time talking about boundary layers. And in particular, we're going to, in the context of boundary layers, we're going to talk about predicting shear forces. So let's take a quick look at the roadmap for this chapter. This chapter describes how to predict shear stress and shear force on a flat surface. And by a boundary layer, I mean this is the region where the velocity changes with respect to the distance from a flat surface, and we'll talk more about that later. The emphasis is on the theory because this theory provides the foundation for a more advanced study in fluid mechanics. So even though this may seem like it's coming out of context here, concentrating on a flat surface, this is definitely kind of a new topic. Shifting gears, but it is a foundation. Boundary layers are very important for fluid mechanics. So what we're going to do first of all in section 1 and 2, this is a video on sections both 1 and 2 because 2 is quite short. We're going to concentrate on uniform laminar flow, and we're going to describe both Couette flow, which we've talked about briefly before, which is a moving plate, one moving plate over another with some fluid in between it. And then we're going to talk about Healy-Shaw flow, which is similar, but it actually has two plates that are stationary and a fluid moving in between them. And we will then that will fold in nicely into sketching out what the boundary layer looks like on a flat plate, and we will explain the main regions of that. And in fact, I think it's instructive to actually start out with that figure. So I actually am jumping to a figure in section 9.2, figure 9.5 here, showing what we're talking about. And so we can see here, this is a thin flat plate running along here, this dark line. And this plate has been placed inside a velocity structure. So in this case, the velocity is flowing from left to right, and it's uniform and steady to begin with. When out here, you would have a very uniform flow and steady flow flowing at what we call the free stream velocity of u naught. But once it encounters the plate, the flow, we know from the no slip condition that the flow has to go to zero at the plate. And so we have a very, very steep velocity profile initially as the velocity starts to adjust to this plate. So we have, because we have a very, very large du dy, if you will, remembering that the shear stress is equal to the viscosity times the rate of shear strain. So this is very, very large right here at the initial point of the flat plate, and so we have a very high shear stress. The shear stress gets lower and lower and lower as this boundary layer develops, and we initially have a very smooth layer, and this is called the laminar boundary layer. So we have this region basically from the beginning of the plate to a point where it starts to get turbulent. That's going to be the laminar boundary layer. And then once turbulence starts to form here, at this point, we reach what's called the critical point, and that's what the critical point is when turbulence starts. And we then have a transition region here where turbulence is begin to fill this boundary layer region. You can see that it starts out small, and then once the entire boundary layer is turbulent, we are in what's called the terminant boundary layer regime. And so we kind of have these three different regimes, and this chapter is going to talk about all of these. And initially, we're going to talk about a laminar boundary layer. So this section is a uniform boundary layer. We're going to develop equations of motion for steady, uniform laminar flow. And this is one situation. This is just an arbitrary situation, actually, where we have A velocity profile, remember, whenever the fluid is in contact with a surface that's at rest, or traveling at some velocity, these have to be, the velocity of the fluid and the velocity of the solid, basically the boundary, have to be the same. That's a boundary condition. And so we don't actually know in this general figure whether or not this plate is at rest or not, but we do know that the velocity of the fluid and the boundary have to be the same. And so we've got this this steady and uniform velocity structure. So this is just this. If you looked anywhere along this blue region, the velocity structure is going to look this way. And the book here analyzes the forces on this piece of fluid here. We've got a little control volume drawn here. So I'm just going to ask, thinking about this, what are the three forces acting on the fluid? What would we think would be important, just from our knowledge of fluids at this point? Well, we can probably guess that gravitational force is going to be important. That's one. There are three forces. We've already talked about the shear stress. We're going to talk. We know that that's so really what we're after here is the net force due to the shear stress tau. And then the final one is the net pressure force, which we've seen before. The net pressure force. So if we go back to that figure again, we can see that these three forces are in fact represented. Let me use the pencil. We've got some shear that's occurring here and here in the volume, because there is a velocity difference across this piece of fluid. The fluid is actually moving slower at the bottom than it is at the top. So there's basically a net shear in the right, going left to right. There's also pressure forces, as we've seen before when we were dealing with the momentum equation. We've got pressure forces acting here and here, and this is acting across basically this unit length here in the fluid. But of course, into the board or into the slide, it's going to also be uniform in that direction as well. So we can define an area and get a net force, a net pressure force out of that. And then finally, obviously, we've got the weight of the fluid and the force of gravity down. And so we can look at these three forces and just across that little volume that or that little dashed area that we sketched out in that figure. And we can see that it's just going to be P delta Y minus P plus a change in pressure with the distance along the plate, dPds, times the length. The length of this is delta S. Okay? So that is going to reduce to being just a change in pressure over this basically this area here, and then we can look at the shear stress, and it looks very similar. It's just the shear stress plus the change in shear stress at the top of the fluid parcel minus that at the bottom, and we get a shear stress, a net shear stress force of d tau dy delta S. And then we in the past we've also looked at the weight. Again, rho times g times a volume is going to be mg. This is actually just an area, so these are force. All of these are force per unit length, and so we end up with this equation here, substituting gamma in for rho g. So basically, this is pressure, this is the shear stress force, and this is the gravity force, just to summarize these. So we can add all these together. These have to sum up to zero. If the fluid, since the fluid is not accelerating, remember this is steady flow, so it's not accelerating. Plus it's uniform, so we know we don't have any centripetal accelerations due to curvature. And so these sum to zero, And these produce what's called the Navier-Stokes equation, which is an extremely important equation in fluid mechanics. And so putting these all together and canceling out the delta S and delta Y's from the previous equations, we get this equation of d tau dy is equal to the change along the path or along the parcel of just P plus gamma z. We should note that we've seen this thing many times. This is just the piezometric pressure. The addition of the static pressure plus the elevation term. So this is piezometric pressure, which we've dealt with a number of times. We've seen this come up over and over and over again. So if we plug in the fact that we know that tau equals mu du dy, we get this equation here. And in fact, we have to take the second derivative of the velocity in order to get d tau dy. So we plug this term into here basically and get this out of the equation, and this is the form of the Navier-Stokes equation that we'll use. So applying that now to Couette flow, you might remember from early on, I think this might have been chapter 2, we talked just briefly about Couette flow, where it was produced by one moving plate. It was a moving plate over a stationary plate or a stationary boundary. In this case, we're looking at horizontal, so there's no pressure gradient, and there are no, and the streamlines are horizontal, so there's no change. There's no ds, dz, ds. So basically, this term right here goes to 0, and this term goes to 0, and we're left with the second derivative of velocity with respect to y equals 0 for this particular situation. Now, what are the boundary conditions? If we think back to Couette flow, what do we have for the boundary conditions? We have that the velocity here is going to be 0 at y equals 0. That's a y. And we have the velocity is going to be equal to capital U at y equal L because this plate is moving. So down here, U equals 0. So we can apply these conditions actually. Let me just do this really quickly. Let me go back. We're basically going to derive this equation right here, but just to show you how this is done, we have to integrate twice d squared u. Let me start that over. I keep wanting to write a y. D squared u dy squared equals 0. So the first integration causes this to be du dy. That's going to be a constant. The second integration is going to be going to give us u, and that's going to be c1y plus c2. So basically, if I just do one of these quickly, the way you deal with this one, for instance, as an example, you move the dy over to the other side, and you have to integrate this, and so out of this you get c1y plus c2. So that's what we get here. So just integrating twice to separate, basically to get the value of the velocity, because that's what we're interested in. Now let's just quickly apply the boundary conditions. So the first boundary condition is that that u equals 0 at y equals 0. Whoops, that's a plus. And so we can see that that gives us c2 equals 0. And applying the second boundary condition, we're going to have u equals c1 times L. Y is now L, and we've already noted that c2 is 0. So this boundary condition gives us the fact that c1 equals u over L. Now that gives us a very interesting result, which we already knew, and that is that that the velocity structure is linear. So oh, let me just go back and say one other thing. Since C1 is U over L, then plugging in back into du dy, that also equals U over L because it equals C1. So going to this equation, we just have plugged in from the boundary conditions, the result from the boundary condition, that du over dy equals U over L. And we have a uniform linear velocity profile for Couette flow. So this gives us a very easy, in uniform laminar flow, this when we have one moving plate over a stationary plate, we have a very simple equation. As long as we know the fluid properties here and the thickness of the fluid, we have a very easy equation to estimate the shear stress. And we can, in class, we will do some examples with Couette flow. The Healy-Shaw flow, on the other hand, is two stationary plates. And so in this case, what are the boundary conditions? It should be fairly simple to figure this out. So think about it for a second while I get my papers switched over here. So the boundary conditions are, at this boundary, we have, let me grab a pencil. We have u equals 0 at y equals 0. And we also have u equals 0 at y equals, in this case, b, because they're using b as being basically the thickness of the fluid in this case between the two stationary parallel plates. So, and this time we are allowing the plates to be angled. It's not horizontal, and so we're allowing for pressure and for basically piezometric pressure to not be 0. So we actually have to integrate this equation, and so we can do that fairly easily. It's the same. Let me just grab a new sheet here. Again, it's very simple to do this. We start out with d squared dy squared, and that's going to be equal to, just go back, 1 over mu d ds p plus gamma z. And if we integrate this twice, knowing that it's steady and uniform, so these properties on the right-hand side need to stay constant, then what we end up with, very similarly to what we did before, we're going to end up with a y squared term, and we get a 1/2 out of it too, so we have 1/2 y squared times everything else on the right-hand side, p plus, and we have the terms that we had before from the integration before when we had just 0. So we still have two constants to determine using the two boundary conditions. So let's go ahead and apply the boundary conditions. U equals 0 at y equals 0. So this term, this big long term here, is going to be 0, and C1 is going to be 0. And again, we get the fact that C2 equals 0 from the first boundary condition. The second boundary condition, again, is that the velocity, again, is 0, but now we're at the other boundary, so we have b squared over 2 mu d ds of the piezometric pressure again, and we now have plus C1b, and we can move this guy over to the other side of the equation. Minus C1b equals b squared 2 mu d ds p plus gamma z. And we can see that if we take the minus sign there, and this is going to cancel one of these. So in fact, this is the equation that we get in the book, and we can see that we've done two things. We've integrated twice in order to get this equation, and we've applied the boundary conditions. So so this is the equation that we get when we plug back in for our constants that we derived, and plugging back in for C1 gives you this equation. So this is the equation for Healy-Shaw flow, and there are a couple of simplifications that can be made. You can plug into this equation. You can plug if you're looking for the maximum velocity. That is going to be determined when, well, let me just ask that question. Think about it. Where is the maximum velocity occurring inside or between these two plates? At what y value? It's occurring right at the middle. So it's occurring at a value of y equals b over 2. So if you simply plug in this equation for y equals b over 2, you're going to get the maximum velocity. And so that gives you this equation here. That also can be reduced to be written in terms of the piezometric head, h, because we know that P plus gamma z, we know that's the pressure, but we can write that in terms of the head by saying that H equals basically P over gamma plus Z. And so if we multiply both sides of that equation by gamma, we get this. So if you note carefully, the difference between these two equations is that there's a gamma in here now, and that we've replaced P plus gamma Z with H. This is an interesting result here, that the maximum velocity is always in the opposite direction of the direction of the head or the piezometric pressure. So in the direction the piezometric pressure is decreasing, that's the direction the velocity flow is going to be in. So let me state that again. The opposite direction, the direction in which the piezometric pressure is decreasing, negative sign, or the piezometric head is decreasing, that is going to be the direction of the velocity. So if we go back and we look at this graphic and we see that the fluid flow is from right to left, then we know that the piezometric pressure and the piezometric head have to be increasing from right to left in the opposite direction of the flow. So the other thing that you can do is you can develop an equation for the volumetric flow rate by integrating over y, integrating the velocity over y. The book shows this, and you can then convert this into the average velocity is just 2/3 over the u max. So that's another equation that we can use. So just summarizing, go back one. These are really the main equations. This and this main equation here, and the kind of the derived equations for the u max and the velocity maximum and the average velocity are really the defining equations for Healy-Shaw flow. Again, for uniform laminar flow. The other thing that we should note is that the Reynolds number now, we've seen this before when we talked about dimensional scaling, is the velocity times b. Remember that this looks a lot like what we were using for the, or we also saw this form of it, of the Reynolds number. And so in this case, L, the characteristic length of the Healy-Shaw flow, is the diameter, or not the diameter, but the distance between the two stationary plates. So these equations, the Healy-Shaw flow equations, are going to apply for when the Reynolds number is less than 1,000. That's basically what laminar flow is. When we get over that value, the kinetic, remember the Reynolds number is basically the kinetic forces over the viscous forces. And so when we get over a value of 1,000, the kinetic energy is dominating over the viscous. So as long as we're staying, the viscous forces are large, we're going to be remaining in the laminar flow regime. So this allows us to solve problems of Healy-Shaw flow when we have flow going between two parallel plates. And here's an example of some oil with a certain viscosity, and it's downward vertical plates, and we can determine the flow and also the pressure gradient through the Healy-Shaw equations. And we'll do some examples of this in class again. So just summarizing now, going into section 9.2, looking at a qualitative description of the boundary layer, we can define what we mean as the boundary layer. And I'll just skip forward here. The boundary layer really is defined by this dashed line. This is what the velocity flow looks like over a flat plate, which is what we've been dealing with here. And normally we define the thickness of the boundary layer. This can be quite arbitrary, but for fluid mechanics, we're defining the thickness of the boundary layer, delta, is being defined as the distance from the surface of the plate to where the velocity is 99% of the free stream velocity. And obviously this is somewhat of an arbitrary term. It turns out that the actual thickness of the boundary layer is sometimes around 2 or 3% of the plate thickness if we inserted a flat plate into this flow field. And so, just summarizing, the boundary layer is ultimately caused by the no-slip condition. That, if I can write it, the no-slip condition is what's causing this boundary layer. Because as the flow encounters the tip of this, the initial tip of the stationary plate, the velocity of the flow has to equal the velocity of that plate. So that is the no-slip condition, whether the plate is moving or not. The fluid, therefore, near the plate must change. And in this case, if this is a stationary plate, it must decelerate. The fluid has to decelerate and go to the speed of the plate. In this case, it's probably equal to 0. So it's got to decelerate quickly. That causes other fluid particles to also decelerate. And so the boundary layer, the adjacent particles, due to the shear stress, they're imparting shear stress onto the other particles around them, and the boundary layer develops and gets thicker and thicker. It thickens until it becomes unstable. This is the critical point, as I mentioned before, here, where we start to develop some turbulence, which we can observe right in here. We're starting to see some turbulence develop. The transition region describes basically the length along the plate where the turbulence is not fully developed. But once the turbulence is fully developed, the entire boundary layer is turbulent. We are now in what's called the turbulent boundary layer. So again, just summarizing, we have these three regimes. The laminar boundary layer, and we just described Couette flow and Healy-Shaw flow that would be for smooth, low velocity boundary layers, and we have a transition region and then the turbulent boundary region. So we're now going to move into subsequent sections to talk about these other regions. And in particular, we'll talk a little bit more about the laminar boundary layer in section 3, and then move on to talk about these other transition and turbulent regions. Okay, thanks.